All right, so we are finally on the last example for this section. We're asked to solve the equation exactly, and we're given cosine squared theta plus 3 cosine theta minus 1, and then we're also given the bounds are from 0 to 2 pi. So we want our final result to be in radians. So let's utilize our substitution here. We're going to let x be equal to cosine theta. That way we can turn this entire quadratic equation into x squared plus 3x minus 1 is equal to 0. And unfortunately, I mean, they give you the hint in the example, but we can't use AC method here. We have to jump straight into our quadratic formula, which is x equals negative b plus or minus square root b squared minus 4ac all over 2a, where our a value is equal to 1, right? It's the coefficient of our x squared. Our b value is positive 3, and our c value is negative 1. So when we plug this in, we get x is equal to negative 3 plus or minus square root. 3 squared is just 9 minus 4 times a times c is just negative 1. So that ends up giving you a plus 4, and then all over 2a all over 2. So we end up with x equals negative 3 plus or minus square root of 13 all over 2. And so it's actually important to note because we're eventually, in probably about a minute or so, we are going to set this x value back equal to our cosine theta. We need to think about, okay, well, what is my range for cosine theta? Oops. My range is from negative 1 to 1. So these values need to be within that range for us to have a defined value, a defined angle measure. And it's not the case that both of these work. If we look at this in decimal form, we end up with negative 3 plus square root of 13 ends up working. That gives us about 0.30278. But negative 3 minus square root of 13 actually gives us about negative 3.3028. And this value is less than 1, less than negative 1. So it's not within that negative 1 to 1 range for our trigonometric function. Therefore, we need to reject this result. Okay. So our only x value that we're looking at is this 0.302, which is our negative 3 plus square root of 13 over 2. And so that's what we're going to set equal to our cosine theta so we can officially solve for all of our potential angles. Right. Now what do? We take the arc cosine of both sides by our inverse cosine function. And so we're looking at theta is equal to our arc cosine of negative 3 plus square root of 13 over 2, which again, what we have in parentheses here is about that 0.30278, which is a positive value. So when we look at our unit circle and our acronym, all students take calculus, we're really honing in on that first quadrant and that last quadrant, quadrant 1 and 4, because these are the only quadrants where cosine's positive. when we compute this, and I'm actually going to compute it in degrees so we can really just visualize where our angles lie and then find our reference angle so that we can find um, that angle in that fourth quadrant. So when we do compute this in degrees on our calculator, we end up getting about 72.375 degrees, which is about, I'd say, here. And so that's also our reference angle, which then tells us that if we were to find our angle in our fourth quadrant, that's just 360 minus that, which gives us about 287, 287.625 degrees. Write that down. And 287.625. So these are our solutions. However, we want to put it in terms of radians to get our final result, and we want to keep it exact. So I'll even write, these are our solutions in degrees. But therefore, our exact solutions in radians are as follows. We just have theta is equal to our cosine inverse -3 plus square root of 13 over 2 and then 2 pi minus this, minus our arc cosine of -3 plus our square root of 13 all over 2. And that is it. Try and create a little box. It's not going to be perfect. There we go. And we are done. I hope this was helpful. This does conclude our section 9.5, solving our trigonometric equations. And we're really in the home stretch here. We're on to our last chapter, chapter 11. And so the next video will be really focusing on distance, midpoint formulas, and our standard equation of a circle. I will see you guys all next time. Take care.